Let's continue our discussion of functions. Are these examples of functions? Take the first one. The domain are student names. The correspondence is with their W numbers. So the range is going to be the students' W numbers. For us at our school, the W number is that personal identification number that each one of you have. So does each student have exactly one W number? Could there be a case where a student has more than one? Well, there shouldn't be a case. If there was, there's been a mistake. Each student should have one uniquely identified W number that matches their name. This is an example of a function. Every student has exactly one W number. Now let's take a look at the domain being the W numbers, that personal identification number. And the correspondence is with a grade in a class, a number. And let's say overall grade. Okay, so we'll make that tiny little clarification. Not a grade on a specific not a grade on individual assignments, but the overall grade in the class. What do you earn at the end? And so here we use letter grades, so it actually is the case that our range does not have to be specifically numbers. We could talk about, just like in the previous example with the locations and the teams, we could have words or names or letters to be our range. So we could have that example of A, B, C, D, F as our range for grades. Is it the case that each W number corresponds to exactly one grade in one class? Right, so we're identifying one class. Is it the case? Well, by the end, you only get one grade, one letter grade. So this one could be a function. Again, there's a situation, if you retake a course, you could improve your grade. If you scored a D or an F in a previous semester, you can retake it for a better grade. But those are specific cases. Let's just talk about first time around grade in a class. Now let's flip it around and look at grade in a class as our domain. So those letters, A, B, C, D, F, and we're going to map the grade to the W number. So now do we have a situation where each grade goes to exactly one W number? Each grade gets assigned exactly one W number. No, not at all. Multiple students could get A's, multiple students could get B's, etc. This is not an example of a function. Two students could have the same grade, so two different W numbers are assigned to one letter grade. That's not a function. In example 4, we have a postal address, so the address of where you live. Given an address, the postal address is going to be mapped to the person living at that address. So we're assigning the postal address a person's name, whoever lives at that address. Is it the case that this is a function? Does each postal address get assigned exactly one person's name? If you're thinking mathematically, you're always trying to come up with what's called a counterexample, a situation that shows that it's wrong, that it's not a function. You're always trying to think of the counterexample. In this case, think about your own home. Do you live completely by yourself so that only you would get mapped to your postal address? Or do you live with other people so that that one postal address gets assigned several different people? 4 range values get mapped to one single domain value. This is not a function. Let's keep talking. Number 5, we have this example of ordered pairs. Ordered pairs are examples of ways we can write functions, meaning that the first value is in the domain and the second value is in the range. So the first value, the input, the second value, the output. So we could rewrite this 1 to 2, 4 to 2, Let's do it this way. 4 to 2, 7 to 3. We can use that same arrow diagram as we did before with the teams and the locations. So there are so many possible answers to this situation. I'll let you see if you can come up with one, and then I'll ask you about it a little later. Another way we can represent a function is with a table. Similarly to the arrow diagram here and to the ordered pair list here in number 5, in number 6 we could list out our ordered pairs or our domain under the X column and our range under the Y column. And we have a question, is this a function or a relation? So is it the case that each value in the domain gets exactly one value in the range? Explain in words why it is or not a function. So looking at the domain values, -2, 5, 0, 2, 5, we have a repeating number here. Let's see where 5 goes. 5 gets mapped to 0 and to -2. Oh no. 5 gets mapped to 2 different values in the range. This is not a function. We can say the input 5 corresponds to more than one output, specifically 0 and -2. So because we have one value that breaks the rule for a function, every input has exactly one output, we don't have a function. The domain, a lot of times you'll see domain abbreviated with a D. We're going to write it as a set. That's that curly bracket. And for the domain, we just list out the numbers that we have, or the values in our domain, without repeating numbers. We don't have to repeat them. We don't want to repeat them. They shouldn't be repeated. So the domain, -2, 5, 0, 2, we already have a 5, so we don't need to write it again. The range, we're going to write our values in the range, 6, 0, -2. -2 gets repeated a bunch. Notice it does not matter that in the range we have 3 inputs being mapped to exactly the same output. That doesn't matter. We could have all the values in the domain go to only one value in our range, and we still have a function. We'll see some of those a little bit later. With our sets of domain and range, it does not matter in what order you write the numbers as long as you list them all out. And so there we have our domain and our range. Question 7 I'll leave for you to think about. Given the following sets, determine if the set represents a function or a relation. State a reason. List the elements in the domain and the range. I'll do part A for you, and I'll leave B and C for you to think about on your own. Part A, do we have a function or a relation? Look at the inputs, the first numbers, 1, 2, 3, 4. They are all different. Because they are all different, we know that there's only one output for each of these inputs. This is a function. Reason, exactly one output for each input. Our domain, we're going to write out those first numbers, 1, 2, 3, 4, all the first values in our ordered pairs. The range, we write out the second values, 2, 4, 3. The last ordered pair has another 2, but I do not need to repeat it. It is perfectly acceptable for both 1 and 4 to get mapped to 2. Just like in our previous example with the baseball teams, both the Cubs and the White Sox got mapped to Chicago, and we still had a function. It's the same idea here. You try B and C on your own. See if you can come up with whether they are examples of functions or relations. Now let's look at vending machines. We've got vending machine at school, a variety of snacks to choose from. Maybe not so great healthy snacks, but what healthy snacks are ever in a vending machine? Some of us know exactly what we want when we're going for a snack in the vending machine, so our choice is based on the food, and then we have to figure out how much money to pull out in order to pay for it. So we have the input is the list of choice of snacks, and the output is the cost. First question, what is the domain? Remember, domain is the set of input values. So our domain are the lists of the snacks. Snickers, Twix, Doritos, gum, cookies, red vines, and mints. Our range is the cost of the snack. $1.20, $1.20, $1, 75 cents, $1, $1, 75 cents. Do we have a function or relation? Does each choice of snack correspond to exactly one price? Yes. And again, notice how the arrow is going from the domain to the range. This is not a double arrow that goes back to the domain from the range. It only starts in the domain and goes to the range. That may help as far as understanding the difference, especially when we flip this around like we will in the next example. Now, what if we only have a certain amount of money in our pocket and I don't really care what I want, I'm just hungry? Now we have a situation where our choice is based on the cost, which then determines what type of food we can get. Now, what is the domain? Domain is our cost. $1.20, $1, 75 cents. Our range is the snack. Snickers, Twix, Doritos, gum, cookies, red vines, and mints. Do we have a function still or not? Does each cost correspond to only one snack? No. Both Snickers and Twix are $1.20. $1 corresponds to Doritos and cookies and red vines. 75 cents goes to mints and to gum. We do not have a function. We only need one input. In this case, all three of them violate our function rule. But we can say an input corresponds to more than one output. And an example, $1.20, both Snickers and Twix. Just as we can use arrow diagrams, ordered pairs, tables to represent functions, we can also use graphs to represent functions. Given a graph, we can identify the domain and the range from the graph and use the graph to evaluate the function given certain values of x. So just like before in previous algebra classes, we had this ordered pair, x, y, and when we graphed, x was along this horizontal axis, y was along the vertical axis. So if we had the ordered pair, for example, 2, 1, let me mark off my table really fast. 2 was for x and 1 was for y. This is telling us a location on this grid. We always start at the origin. That's in the middle where these two axes cross. Think of these two axes like two number lines. We have a number line for x and a number line for y. And so if I think about them as number lines, x being 2, y being 1, I'm really looking at the place where if I extend them vertically and horizontally, I find that 1 point, 2, 1. Backing up for a moment, if I were to graph that point 2, 1 on my grid, start at the origin, I go 1, 2 on the x-axis in the x direction, the horizontal direction, and then I go in the vertical direction. It says up 1, so I'm going to go right there, and I get that ordered pair 2, 1 as a point on the graph. If I have a list of these points, I can plot a list of these points onto a coordinate plane and talk about whether it's a function or relation. If I have an equation, which we'll get to a little bit later, I can also create a set of ordered pairs and be able to graph. So some of these graphs are coming from equations because they have infinitely many points. One great thing about graphs, once we have a visual of our function, we can use a technique called the vertical line test. If we draw vertical lines on the graph, those vertical lines should only intersect the graph in at most one place. I'm going to change this wording for now. Not exactly one place, but at most one place. We could have a situation where they don't intersect the graph at all, and you'll see that in just a moment. As an example, we take the first graph. This is a graph of an ellipse or an oval, and we can draw vertical lines. And my vertical lines aren't perfect, but the idea is we draw vertical lines on the graph, and then we look. How many times, looking at one vertical line, how many times does one vertical line intersect the graph? I'm intersecting the graph in more than one place. We can draw lots more vertical lines. In this vertical line I just drew, I only intersect the graph once, but it only takes one to create a problem. So here I have a vertical line that intersects the graph in two places, so I do not have a function, and I have a relation. So the vertical line, we can say the vertical line intersects the graph in more than one place. Similarly, on graph number 2, we can play the same game, vertical line, vertical line, vertical line. And we don't have to do this actually. We can do it mentally, but sometimes it helps, at least in the beginning, to physically draw these vertical lines. And then we look, how many times does the vertical line, each vertical line, intersect the graph? Notice I have a few on the outside extremes that I'm erasing that don't intersect the graph at all. Hence my change to at most. But the ones that are left, they only intersect the graph one time. Each one of them only hits the graph once. This is an example of a function. So I'm going to leave 1 on here. We have a function. And the reason here, all vertical lines intersect the graph at most once. Given the graphs of these functions, we can talk about domains and ranges as well. I'm going to erase my vertical lines for now. Domain is going to be represented by the x values. The range is represented by the y values. So if we were to list out all of the ordered pairs, by the way, we cannot. There are infinitely many of them. But if we tried to list out all of those ordered pairs, we would peel off all the x values, that would be our domain, and then we would peel off all the y values, and that would be our range. Since there are infinitely many, we don't get to write them out, but we can create inequalities that will allow us to talk about the domain and the range. The first thing I want you to do is think about this ellipse, and for the domain, take all of these values. We're going to smash the graph onto the x-axis. Okay? Almost like a panini press. If you've ever had a panini press sandwich, we're pushing from the top and from the bottom to squish the graph onto the x-axis. For the domain, we can smash the graph onto the x-axis. When we do that, and we smash it, we get just the values between -2 and +2. So our domain is all of the x value numbers between -2 and +2. We can write that as an inequality because we're talking about x values. We're going to put x in the middle for this situation. X is between -2 and 2. So -2 is less than or equal to x, is less than or equal to 2. A quick note about inequalities. if you're creating an inequality like this one that we just wrote here, the inequality symbols must be facing in the exact same direction. Because if I cover up any one piece of that inequality, I have to make sure that the inequality statement is true. So use your finger and cover up the x. Is it true that -2 is less than or equal to 2? Yes, it is. So this is good. Let's talk about the interval now. Interval notation is shorthand for a number line. So if we take this graph and we just look at the x-axis, from -2 to 2 are the values that I have in the domain. I'm including -2 and I'm including 2. So in past classes you may have used solid dots to indicate that we're stopping at -2 and 2, but we're also including them. Some classes you may have used brackets to indicate that inclusion. We're going to use brackets to indicate the inclusion because those brackets directly translate to interval notation. Basically, we're getting rid of the number line itself, and we're only keeping the essential elements that tell us what interval we're on. So we started at -2, we end at 2, the brackets tell us we include both of those values. That is going to be our interval notation for our domain. Now, let's talk about the range. This time, instead of smashing it onto the x-axis, think of a trash compactor. Pushes together from the sides. Or if you're a Star Wars fan, the very first movie, when they rescue Princess Leia and they're stuck in the trash compactor. The walls are caving in, they're moving towards the middle. The same idea here for the range. And again, we see once we smash this ellipse in on the y-axis, we get values that cover that y-axis from -1 to +1. So again, just like we did for the x, we can write an inequality from -1 to +1. This time, instead of using x, I'm going to use y to indicate the domain, since we are on the y-axis. And then similarly, we can also create that same interval notation, 1 and -1. We've got all the values between, and we're including those endpoints, either with that solid point or with the bracket. When we write interval notation, we need to rotate this so that the smaller number comes first. Interval notation is always smaller number and then larger number. And so we end up with an interval of -1 to 1. See if you can come up with the inequality and the interval for our function in number 2. I'll have the answers on our OneNote so you can check. And we'll take a look at the next examples in the next video.